Hello, and welcome to our next episode of our video series with Consulting Specifying Engineer. I'm Amara Rasgus, and I'm excited today to be with Russell Senesac of Schneider Electric. Hi, Russell.
Hi, Amara.
All right, so Russell, you started your career in 1996 with APC, and you've moved around quite a bit over the past 25 years. You've held several different positions, including sales, product management, strategy, pretty much you name it. Your concentration has been a lot on mission critical applications, but these days it sounds like you're broadening your focus quite a bit to talk about the new and rapidly developing new energy landscape. And that includes electrical source management, distribution, and load prioritization. And we're going to be talking a little bit about that today. So Russell, let me ask you. So we've talked about the adoption of battery energy storage systems and the market drivers. We've talked about the desire of use not only for economic purposes, but for resiliency within the building overall. And it's clear that BESS must be connected differently than a traditional generator, for example. So we did some research a few months ago, and about a third of respondents said that they were assembling various components to effectively install BESS systems for resiliency. Can you help us understand a little bit more about what's different, versus generators, for example?
Yep. Yeah, this is a very well timed survey that the Consulting Specifying Engineer did, because I think I've mentioned in other podcasts that the amount of adoption and the exponential adoption of battery energy storage systems is something that we think is even going to continue to increase. And so what gets real interesting real fast when you start adding these types of systems to an electrical one line is this desire to use the batteries for something else other than the economic optimization, right? So when I say economic optimization, I'm talking about, hey, they're tied with the solar, and when the sun is out, we don't use all the energy. We use the batteries to be able to supplement. So we charge the batteries, and then when the sun goes down and we need the power, we discharge the batteries. So it's more of an economic type of equation that you're using them for. What gets very interesting very quickly is that, hey, can I use them for resiliency? If the power were to go out, can't I go to the battery? And if I have a generator, can I go to the battery first, potentially? And what gets real interesting for the specifying engineer very quickly is how do you actually create that resiliency, that isolation for resiliency that a battery requires? And we're going to talk a lot more about that in this podcast, but I thought it would be good to maybe lead with just this piece that basically says, either we're relying on some foreign or domestic type manufacturer of inverters to be able to create isolation that is rigorous and robust, the same way we've come to look at like UL standards for, let's say, transfer switches, or you can see about that third down there, that 35%, we're basically asking the engineer to figure it out, right? Build something that isn't necessarily well defined in order to be able to create that isolation that's required for resiliency. And so, and the interesting question is, what's the 12% other doing right now? We'll have to dig into that one a little bit, but yeah, I think this starts to highlight the storyline, which basically says resiliency is required. You need isolation to do it. How do you make that happen? And so I think we can talk a little bit more about that as we go in this podcast.
Yeah, that's a good point. And so we understand that this is normally grid tied. Batteries are grid tied, generators are not. So what's an overview of the sequence of operations, or how does this all get put together?
Yeah, so this is this isolation versus transfer. It's really kind of like a fundamental change in our electrical one line that we've known for decades, meaning that we primarily, for emergency systems, had two sources: the utility and some sort of reciprocating engine generator. And we've had a transfer switch that was connected to the two, and the transfer switch does exactly what it's titled, right? It's an automatic transfer switch where it is transferring from one power source to another for a certain requirement, right? So that certain requirement usually is utility loss. but you can program ATSs, obviously, if you want them to transfer and do different things. They're very programmable. But primarily, it's been power goes out on one side, you get power on the other one, transfer it over, and then when the power returns to the what we call normal side, you transfer it back. So there's a lot of very standard defined code and regulation around how that ATS works. And we've been doing it for, like I said, decades. So we've been getting more refined over those decades, right? Like as we learn new things, we make it even more robust as we go. I think the major difference now is that if you look at the right-hand side of that slide that's up on the screen there, what you'll see is that a battery energy storage system behaves differently, right? So a battery energy storage system is normally connected to the load and to the grid. And that's not true with generators. Generators are typically never connected. I don't want to say never, right? So I'll say typically never, because there are very unique corner cases, right, where somebody does want to do some sort of peak shaving or something like that with a generator. But just in normal operations, the bell curve, you don't connect them. And so when you look at a battery as being normally connected, when that utility fails, now that battery has to have a way of disconnecting from the grid in order to be able to create energy that the building can use. Because if you can't isolate yourself or disconnect from what you're connected to, you're trying to start everything instead of just the building, right? And so you don't have enough power to start the grid. Like you can't start your house and your neighborhood block all at the same time. You got to isolate from the neighborhood block, get it to something that you can work with, which is just your building, and then you can create energy in order to be able to power the load. So if you walk through the idea of how the battery energy storage system would work, it would be similar to normal. I'm connected. I might even be net metering. So if I'm connected with solar and the sun is high and I'm creating more energy than I need, I may actually be selling power back to the utility. But now all of a sudden a lightning storm comes along and takes out a power pole, and now the power goes out. So now the power's gone out, but I'm still connected, right? And so now I know that I want to disconnect because I want to be able to create energy for my building so I can turn my building back on. That's when you need that switch to open. So normally connected, power goes out, now I open the switch. So when that switch is now open, now the battery and the inverter know, hey, I'm isolated, so now I can actually create power for the building. And that's what it'll do, is it'll create power for the building with that switch open. And that switch will remain open until the power comes back. Now, when the power comes back, that inverter and that battery will know that the power came back from the switch, which will then say, okay, stop making power. And now I'm going to reconnect you back to the grid. So it stops making power. I reconnect it back to the grid. And now I'm back to a normal grid following connected scenario. So it's really trying to make sure that you fundamentally understand the difference between a transfer switch and an isolation switch, because a transfer switch, just like we said, one source or the other source. Isolation switch, normally connected, power goes out, open. So this open mechanism is much different than the transfer mechanism. I'm very good with my hands. So I think actually, Amara, we've got a slide here that we could probably pull up for our users. Yeah. So very much in the industry, the idea of an automatic transfer switch, ATS, is the nomenclature that's very well known, right? I know what an ATS is, automatic transfer switch. We believe in the future, there's a new category of switches that are going to be required, that are going to be needed for this isolation with battery energy storage systems, right? So instead of an ATS category, there will be an SIS category. And that source isolation is exactly what it's described as. You have sources, right? Could be battery energy storage systems. It could be other different sources, right? And isolation, open, close, right? Very simple operation, not transfer different, isolation. So the way we should be thinking about this as an industry is that, hey, when I need a generator, I need an ATS. When I decide that we're going to implement a battery energy storage system, it's not an ATS anymore, it's an SIS that's required. And the idea behind this now is that SIS is going to go through the same level of rigor and robustness and testing and certification that we've spent decades on perfecting for an ATS. Because if I'm using that that battery either in place of or before a generator, and it's just as critical to provide power. It's just as critical that that isolation switch has the same level of endurance and testing that the ATS has historically had.
Wow, well, you covered a lot there, Russell. Thank you. I do appreciate your time. Today, I've been speaking with Russell Senesac from Schneider Electric. I do thank you for your time, and we'll see you on our next video discussion. Thank you and goodbye.